In this video, we are going to introduce a new type of function called a piecewise defined function. And I think it's best to introduce these new functions by looking at an application where we actually see a situation that is a piecewise defined function. So let's take a look at this introduction. Suppose a car is stopped at a red light. Once the light turns green, the car accelerates at a constant rate for 10 seconds until it reaches a speed of 45 miles per hour. Then the car travels for 30 seconds at this constant speed of 45 miles per hour before decelerating for 20 seconds as it comes to a stop at another red light. So you can see what's happening if we look at the different pieces of this graph. Since this one is already graphed for you to give you a visual, you can see that the car begins stopped here at that red light, and then the light turns green and the car accelerates. So this portion of the graph is when the car is accelerating at a constant rate, and it accelerates for 10 seconds and it reaches that speed, it says right here, of 45 miles per hour. But then we have a change because now it says the car is traveling for 30 seconds at a constant speed of 45 miles per hour. So this portion of the graph represents the constant speed, again, of 45. And you can see that that occurs right here from 10 seconds until 40 seconds, and that's a total amount of time of 30 seconds. But then we have a change again, because now the car is going to decelerate for 20 seconds until it eventually comes to a complete stop at another light. So that would be this portion of the graph here. The car is slowing down, it's decelerating, and that's going to happen for 20 seconds. So you can see from 40 to 60 seconds, that's 20 seconds, and then eventually it comes to a stop right here where you can see that the speed is 0. So hopefully this visual helps you understand why we call these piecewise defined functions. Sometimes we just say piecewise functions for short, because you can see that this total graph has 3 pieces. The behavior of the graph doesn't remain consistent. It changes, and we have these 3 different pieces, and therefore they're all defined by different individual equations. So we're going to try to write equations for each of these 3 pieces. Let's start with the variable key. So we can see we're keeping track down here along the x-axis. We're keeping track of our time. So this is time. X is equal to basically time, but it's measured in seconds. So timed, measured in seconds is the amount of time that the car has been traveling. I'll just say time measured in seconds. And then our output along the y-axis here is going to be our speed. Now, you could write y if you wanted to here. I'm going to also write f of x because those are my output function values. And those outputs, those are the speeds specifically measured in miles per hour. You really want to be detailed with your variable keys here. So we're putting in a time measured in seconds. We're getting out the speed of the car at that time measured in miles per hour. So when you go to write a piecewise defined function, you'll see that you have the name. This is the name of the function here. We're just calling this function f of x. We're not being very creative. And then you see that you have a big curly bracket here. We're opening up the function because this function contains 3 pieces. So essentially, you're going to have 3 different equations here that correspond to each piece of the function. And then you're also going to have the individual domain restrictions written at the end of each piece. So these are going to be our 3 different domain restrictions here. It's going to be the domain restriction that applies to the individual piece. So let's begin with the red portion of this graph. So I'll do this work in red to correspond. So the red portion of the graph, we notice that it is linear. It's a line. And if we want to write the equation for a line, then we better know the slope of that line. So you can see that we are going to rise 45 miles per hour. And then we go to the right, or we run, and we're running at that time of 10 seconds. So if we look at the slope for the first portion of this graph, we're basically going up 45 and to the right 10. So we're doing our change in y over our change in x, and of course, if we simplify, that's going to be a slope of 45. And then it's good to notice that the y-intercept here of this graph is indeed 0. It goes to the origin. So the equation for this red portion of the graph would be y is equal to 4.5x. Technically, you have plus 0, but we know we don't need to write plus 0. We're just using slope-intercept form. Y equals 4.5x is the equation for this first piece, the one that's in red. So when you write the piecewise function, you don't have to write the y equals part, because remember, that's what f of x is for. The name of the function, we're calling it f of x, but that also represents y. So we have y equals. So we just have to put the 4.5x right here. This is our first function piece. Now, it's important to notice that this red portion of the graph, it was only applicable for the times between 0 and 10. So that's going to be our domain restriction. That comes after the word if. So 4.5x only works if our speeds, which are the x values, if our speeds are in between 0 and 10 seconds. So we'll put x in between 0 and 10, and then we need to put the appropriate inequality signs here. The way we would read this from left to right, we would say 0 is less than or equal to x is less than or equal to 10. And what that really means is that x is greater than equal to 0 and also less than or equal to 10. That means that the times are in between 0 and 10 seconds. And for any time between 0 and 10, we're going to go ahead and use the equation y equals 4.5x. First piece done. Now we move on to the second piece of the graph, which is the piece that I have highlighted in green. Now this is just a horizontal line. It's constant, a constant speed of 45. So the equation for that horizontal line is just y equals 45. So in our piecewise defined function, we have y equals 45. Once again, we don't need to write y equals because we have f of x equals here. So we just write 45. But again, that green portion of the graph, it was only applicable from 10 seconds until 40 seconds. So those are going to be x values between 10 and 40. And now we're going to do less than x and less than 40. We're not going to put an equal to here because we put the equal to's on the piece above. And we don't want to have an equal to on both. Remember, to be a function, we want to have one input and only one output. So we don't want to be able to put 10 into this function more than one time. So that's why I'm going to include 10 on the top piece, but I'm not going to include 10 seconds here on the bottom piece. And the same is going to go for 40 as we move on. Now our last piece is the blue piece. And this is the part where the car is decelerating for 20 seconds until it comes to another stop. And so now we need to consider our slope because the slope is different here. So now we're going down a distance here of 45 and to the right 20 seconds from 40 to 60. So if we're going down would be a negative 45. That's my change in y. And then we went right a distance of 20. That's my change in x. So we'd have negative 45 divided by 20, which would simplify to negative 2.25. So we have a slope of this blue section of the graph of negative 2.25. However, this graph, the blue graph, it does not go through the origin. So we need to determine the y-intercept of this graph. So you could use slope-intercept form. You could use y equals mx plus b and try to find the b value, which is the y-intercept. Or this would be a good time to use point-slope form, which is y minus y sub 1 is equal to my slope, m times x minus x sub 1. So I know my slope is negative 2.25. If I'm going to utilize point slope form, then I just need to find a point on the line. So you could either use the point up here, which is 40, 45, or you could use this point down here, and that point is 60, 0. Either point will work because they both lie on this line. So I'm going to go ahead and use the point 60, 0 and set up my point slope form. So that would be y minus the y value of my point, which is 0, is equal to my slope, which is negative 2.25, times x minus the x value of my point, which is 60. So you could leave it like this. If you want to go ahead and distribute this negative 2.25 because you want to look at this equation in slope-intercept form, that's easy to do. So go ahead and distribute the negative 2.25. So we'll multiply the negative 2.25 by 60, and I believe that will give us positive 135. So the equation for the blue line is y is equal to negative 2.25x plus 135. And in our piecewise defined function, again, we don't have to write the y equals because we already have that. We'll just have negative 2.25x plus 135. But this blue section is only applicable, remember, from 40 seconds to 60 seconds. So for only times between 40 and 60, so that would be 40 is a less than or equal to x is less than or equal to 60. So notice again, I'm including 40 for this piece, and that's because I did not include 40 in the piece above. So I want to include those times in one of my pieces, but not multiple, not both pieces. So there you go. You wrote your first piecewise defined function. This function happens to have 3 different pieces, and now you can see what the function looks like as well as what the graph looks like. Now these last 2 questions ask us to evaluate f of 5 as well as f of 60. And I want to show you how you can do that on the graph as well as using just the function. So f of 5, remember, is asking you to put 5 into the function. In other words, if 5 is my x value, we're looking at a time of 5 seconds. So if we were to go on the graph to approximately 5 seconds, then we're trying to find the output, the y value. And you can see there is a little bit of a drawback to using the graph because you might not be super accurate. You might just be sort of eyeballing what this y value is. It looks to be between 20 and 25. Yes, it's going to be 22.5, but you're just looking at the graph to figure out the y value. And sometimes there can be room for error there. So to use the function, you have to find the appropriate piece where x equals 5 belongs. In other words, you're looking at the domains, trying to figure out where does x equal 5 belong. Is it the top piece, the one in red, the middle one in green, or the bottom one in blue? And the answer in this case, of course, it's going to be the top piece, the piece that is in red, and that's because this top piece is for only x values between 0 and 10, and 5 is a number in between 0 and 10. So we're not going to be using the middle or the bottom pieces, we're only using the top piece. That means we're plugging 5 into 4.5x, the top piece. So 4.5 times 5. And sure enough, that does give us 22.5. And then don't forget the appropriate units because we are looking for an output. In this case, that's a speed. So that would be a speed of 22.5 miles per hour. That's going to be the speed at 5 seconds. Now, f of 60 is saying now we want to let x equal 60. So looking at the graph, you can see that x is equal to 60 right here, and the y value is going to be 0. So we're expecting an answer of 0, but let's get that answer now from our function. So we have to think about where does x equal 60 belong? Again, looking at your 3 pieces. It's not the top piece because that's only for x values between 0 and 10. It's not the middle piece because that's for x values between 10 and 40. It's going to be the bottom piece. This applies for x values between 40 and 60, including 60. So this means that we are going to plug x equals 60 into the bottom piece of our function. In this case, that's the equation 2.25x, so we're multiplying that by 60, plus 135. And you know, I'm realizing there should be a negative there. I'm hoping that I just erased it earlier. But please go back in. If you didn't have the negative on that third piece, it should have been negative 2.25x plus 135. So make sure you have that negative. And again, we're expecting an answer of 0. It's really nice to see that we do get an answer of 0, which means that our function is correct, and it does indeed match what we expected to get from the graph.